the second thing we're going to talk about here is resonance. Now, for resonance, we won't be talking about the mathematics of it at all, because the mathematics of resonance are actually quite complicated. But the idea behind resonance is actually very simple. You have an oscillating system, but you are driving it, or applying a force to it, at the same or near to the same frequency that it oscillates at. Wow, I cannot type today. Now, you can see this in a physical system. If you take a pendulum, oscillate it so that it moves back and forth, and if you shake it back and forth in time with the oscillation, what you'll see is actually a growth of the amplitude. In other words, it'll oscillate back and forth more. Now, qualitatively speaking, if you were to take a look at something at resonance, if you drive it along or near to the natural frequency of the resonance, what will happen as time goes on is your oscillation amplitude will grow larger and larger over time. So basically, effectively, it is the opposite of damping. Now, resonance is actually a relatively important property because these oscillations indicate that there's an interaction present. And interestingly enough, this idea of resonance explains a lot of things that are in fact incredibly biologically relevant. Most notably, it explains very, very easily why things like chlorophyll absorb certain colors of light only. And the reason for that is really simple. Chlorophyll has an equilibrium structure. Its equilibrium structure, or at least the equilibrium structure of its light absorbing component, has frequencies that it wants to oscillate at, and if incoming light drives it at the same frequency that it wants to oscillate at, its molecules are able to vibrate back and forth more effectively, which allows it to absorb energy. Now, chlorophyll, reasonably speaking, is a relatively complex molecule. Right? It can have multiple resonances, and these resonances don't have to be necessarily super tight on particular frequencies. But the idea is if you take a look at, say, chlorophyll B, I can tell you right away that if it absorbs light at these two particular wavelengths or colors, so this is like bluish, and this one here is like reddish, these are actually pretty close to the natural frequencies or of the elastic chlorophyll molecule. Right? So basically, if the natural frequencies of chlorophyll are here and here, this is directly going to correspond to the maximum amount of light they're going to want to absorb. Because you get the most absorption or the most transfer of energy or the most increase in the vibrations of what you're dealing with when you're actually absorbing energy from the environment. Right, and this further illustrates the point that resonance is kind of the opposite of damping. Here, we're gaining energy from the environment and putting it into the form of a rotation. And so basically, this explains why systems will only absorb certain frequencies or vibrations of light. It explains why, if you vibrate something back and forth, like moving a spring back and forth, and just shake it at the same rate that it's vibrating at, you can get the amplitudes to be very large. Now, this is probably the most relevant biological example, but even in the cases of simple absorption, you can actually, if you know the damping coefficients, because interestingly enough they do matter here, as well as the natural frequencies, you can predict the exact shape of this. In fact, one thing I will tell you is the peaks are going to tell you where the natural frequencies of your molecules are, and the damping coefficients are actually related to how wide these peaks are. So this first peak of chlorophyll B here has a much lower frequency or damping coefficient than, say, if we were to look at these almost three peaks as if they were a single thing. So you can actually mathematically relate these things together. Again, not the scope of the course, but most of these things are well modeled and well understood. Now, we can also look at a physical resonance. So what I'm going to bring up on screen here is a video of probably the most famous instance of physical resonance that's possible. And interestingly enough, it has to do with a bridge. And this video is absolutely insane if you take a look at it. Like, you can't even believe it when you watch it. So what we're going to take a look at here is a video of the Tacoma Bridge, a rather famous bridge that's brought up in a lot of engineering classes because it demonstrates what not to do when building a bridge. So what you'll see here is this bridge is going to vibrate at resonance. So what you'll see here in the middle of the screen is actually the bridge experiencing a resonant force applied to it. Yeah, that's an actual road made out of concrete too, if you look in the center. And the idea here is the wind just happened to blow at the proper driving frequency that it created a resonant system with a literal bridge. Right? So not only can this apply to small systems or systems that you can hold in your hand, it also applies to larger systems. All things that undergo simple harmonic motion can experience resonance if they're driven at the correct frequency. So here's another side view of it. Uh, Again, nobody's really on the bridge, and then at some point the bridge falls down. I don't know if they actually show it falling down here. Oh yeah, there it is. So we'll skip ahead to it. Nope, we spoiled it. All right. So eventually the vibration becomes so large that it just breaks the bridge apart. I don't believe anybody was hurt on this bridge because if a bridge is moving like that, typically speaking, you'll get off. But resonance can apply to a whole bunch of systems because, again, every system that has an equilibrium and wants to restore itself to it will undergo simple harmonic motion. All these systems have some form of damping associated with them if they're realistic, and all of them can be driven at resonance. It really doesn't matter what thing you're looking at.